Okay, problem 5. This one jumps around a bit. On a scale from 1 to 10, this is probably an 8 as far as our class is concerned because of how many things we have to keep track of. Okay.
Oh yeah.
So here we're looking at the picture, right? We have an airplane. It lands. It coasts for a while, right? And then at this point, it applies its brakes. All right. You'll notice that there's like a little arrow. Should remind you of something. And this is going to go ahead and represent deceleration because it's gonna apply the brakes, and as it's applying the brakes, it slows down to the point when this becomes 0. Okay. Now, so here we have it. The plane travels at a constant speed for 1 second. Let's start labeling some things. So when it actually makes contact with the floor at this point right here, the V naught is going to be 71.5. But it's going to coast for a whole 1 second. Meaning if it's coasting, right, cruise control, the acceleration is 0. So spoiler alert, you also know what the final velocity is at this point. It hasn't sped up or slowed down. It just goes ahead and does that. Now this is real life because if you were to go ahead and apply the brakes immediately upon it landing, you're going to go ahead and create too much friction, and there's a change in momentum that's too strong, and the plane will actually flip over, and well, you get the idea. So let's just focus on this part right here. Don't worry about a part, what they call B. Let's focus on A, which is the coasting distance, right? So in this case, it's not accelerating. So remember, if you didn't catch us last time, we only use the kinematic equations in circumstances where acceleration is happening. Acceleration is not happening in the first part of this problem. So I'm not going to use a kinematic. What I will use is that basic thing, right? That remember that V is equal to x over t. And if I get x by itself, I get tv. Okay. We only use this if acceleration is 0. Hint, acceleration is 0. This is going to work out for us. All right. This is going to give us the coasting displacement. How much it travels while it's coasting. Well, we know it's 1 second. We know it's 71.5. We know the seconds cancel out. We're left with meter, which is the correct unit for displacement. No big surprise here, kind of disappointing, but the coasting distance is 71.5 meters. It's almost like that video from back in the day when the newlywed husband asks his wife, like, if you drive 80 miles per hour in 1 hour, right? Same thing here, right? If we go 71.5 meters per second for 1 second, okay, how much would you have traveled? Well, there you have it, okay? So let's keep this in mind that the displacement as it's coasting is 71.5 meters. That is the distance from here to here. What we must do now is find out how much distance it took to go ahead and once it started applying the brakes. So remember, at this point right here, the velocity was 71.5 because it was going 71.5 meters per second, and then it applied the brakes. It applies the brakes. We have the acceleration. Okay, this acceleration is opposite, so it's going to be negative 4.47 meters per second squared. We have acceleration. We're going to use a kinematic. We know the final velocity at this point, and we want the displacement. We want delta x. So if we do our 5-3-1 thing, we list all 5, right? V naught, A, delta x, t. We have V naught, we have acceleration, we want delta x. We don't need time. Okay, so we listed all 5, we identified the 3, and we identified the 1 variable they're looking for. How do we know? They want the displacement. This is best modeled by, spoiler alert, the third kinematic. It's very important that we have all the signs correct on this problem. Otherwise, it will not come out right. I want to get the delta x by itself. I would subtract the v naught and then divide by 2a, just for the sake of time, because we've done this before already. All right, so this, by the way, let's be clear on this. This is the braking. Up here, we found the delta x, the displacement, while it was coasting, while it didn't apply the brakes, while acceleration was 0. Now, however, it is applying the brakes and it is slowing down. We plug in the appropriate numbers. So v is 0, v naught is 71.5. This is a minus. And then acceleration, this is very important. Make sure it's negative, negative 4.47. Because here's what's going to happen. This is going to be a negative, and up here you have a negative, and the two negatives will cancel out at the end in the calculator, and it's going to give you a positive answer. This is displacement. Displacement needs to be positive. It's not a vector. It's a scalar. It's just a number. It's an absolute value. Okay? So there is no negative displacements. This has to be positive regardless of what happens. So that's why these signs are so important. Okay? Plugging this into the calculator, we end up getting delta x break. The braking distance is 571.8 something meters. The question asks for the total. So the total is going to be the braking distance plus the original coasting distance. So that's going to be 571.8 meters plus 71.5 meters. And we're going to end up getting 643.3 meters. Wow. So this is pretty much two problems in one, right? We went ahead and had the coasting distance where we used the definition of velocity because it wasn't accelerating to find out displacement. And then for the second part, because there was acceleration, right, it was slowing down, we went ahead and had to use a kinematic for that. I would strongly suggest a problem like this, it would be good to maybe pause and just kind of reflect and try to talk it out. Maybe look at the screen right now, pause it, and try to re-explain verbally to yourself what each part represents and how it got there.
Most impressive.
You're welcome.
Perfect.
Problem 6. Sakazi. Sakazi is learning to ride a bike without training wheels. What a beast. His father, more of a beast, pushes him with the constant acceleration, right? And you have all these numbers. We want, again, Sakazi's total displacement. So this should remind you of what we just did a few minutes ago, right? Total displacement means I'm going to have two different numbers to probably add at the end. We've also attached a motion diagram for your consideration. I want to do this two different ways. I want to first do this with equations.
Most impressive.
And then I want to do this with the graph. I'm going to do is get the same answer twice. You don't have to do this twice, right? But I'm going to do it twice to show you that there are multiple ways to get the same answer, okay, as long as you understand. So in this first case, we'll notice that, at first he is being accelerated. So here's the end, right? His father pushes him with the constant acceleration for this much. Okay, he starts from rest, right? So we have the part where he's being pushed by his dad. And then we have the part where he continues on his own. So being pushed by his dad, he is being accelerated for this time. And he starts from rest. And we want the displacement. We want to know how far he goes. If I use the second kinematic, you'll notice that because V naught is 0, this whole term cancels out. Plugging in those numbers, we get 9 meters. So while he's being pushed, right? Let me do this with the. So while he's being pushed, right? I have this color coded with the black. While he's being pushed, he ends up traveling 9 meters. Now, what about when he is doing it on his own, right? Which I have in green. Well, he's traveling at they tell us 3 meters per second for 6 seconds. But he's continuing. He's going constant. It's constant velocity. There's no acceleration, right? We used, when he was being pushed, he was accelerated, so we used a kinematic. In this second part, he's not being pushed, and he's not speeding up or slowing down. So we're not going to use a kinematic because there's no acceleration. We got TV again. Seconds cancel out. I get 18 meters. So what happens is he traveled 9 meters while being pushed by his dad, speeding up, and then when he did it on his own, he went for 18 meters. If you add those two together, that gives you the total that he traveled. He traveled 27 meters before he went ahead and, Well, first law took over, right? Okay, so 27 meters, that's great. Check it out. Graph. Look at this graph. If we were to find the area of this triangle and add it to the area of this rectangle, we would get displacement because it's a velocity versus time graph, right? So for number one, I have a triangle, right? Triangle plus rectangle. For the triangle, I have 1/2. The base looks like 6. And then the height looks like 3 meters per second. The rectangle looks like it's 6 seconds, right? From 12 to 6 is 6 seconds. And the height, again, is 3 meters per second. Well, 6 times 3 is 18. Half of that is 9. And the seconds cancel out. And then 6 times 3 is 18. And the seconds cancel out. And I get 27 meters. Now, there's no doubt about it. I mean, obviously, if we have a motion diagram, area is the fastest way to get the answer. Notice that it's the same answer like we got before with all the equations, right? So if you actually are good at motion diagrams, you could even make your own and solve them this way. I'm not against it at all. Okay? Either way, we got the same answer. Must you do both ways? No. Okay, but I'm showing you that both ways it worked out. What are some things that you need to be careful with when solving kinematic problems?